Hello, my name is Samuel Punch, and today this video will present one element of my thesis, Noise Adaptive Dummy Gate Obfuscation, or NADGO. This is a control framework that actively detects and limits information leakage in quantum cloud orchestration. I'll explain the threat model, how the leakage score works, the enforcement loop, and the results from both simulation and emulation. So let's look at the NADGO threat model. We assume a semi-honest cloud provider. The adversary can see metadata such as job timing, batch size, and resubmissions, but not the quantum payload itself. Their goal is to infer hidden details like the algorithm or its depth. The trusted part is the hardware execution. The untrusted part is the orchestration layer, where leaks occur and where NADGO intervenes. The key novelty of NADGO is the leakage estimator. The core signal in NADGO is a leakage score calculated at every interval. We compare current threshold patterns to a locked reference distribution that was built under our padding scheme. If the current behavior drifts away from that reference, the score rises. It updates quickly, is conservative by design, and supports hard thresholds. The NADGO enforcement pipeline operates directly in the orchestration loop. First, dummy unitary padding locks the execution cadence. Second, a particle filter adds queue-aware jitter to hide timing patterns. Third, the cask router balances fidelity and leakage risk when choosing a backend. Fourth, the leakage monitor enforces a dual threshold, continue when safe, reschedule when close to budget, and abort if the kill threshold is passed. Finally, all actions are recorded in a hash-chained audit log for accountability. The NADGO Tier 1 simulation setup. Tier 1 uses simulation to stress test leakage control without hardware quirks. The workload includes QAOA, TFIM, and VQE at 8 and 16 qubits. Noise models include drift in relaxation times, 2 qubit gate errors, crosstalk, and bursty arrivals. We compare 3 cases: no privacy, a basic kill switch, and timing protection with jitter plus padding. The metrics we use include leakage score, latency, power proxy, abort rate, and runtime overhead. Now that I have outlined the simulation, let's examine the results. The leakage distribution plots show the leakage score distribution under different policies. With no privacy, the distribution shifts high and overlaps with thresholds. With a simple rate limit, the spread narrows but attacks still leak. With full timing protection, the distribution is clearly shifted below the budget, meaning far fewer dangerous intervals. This is why NADGO's padding and jitter makes a difference. Here we see that actions the system takes. The heat map shows abort by qubit count and attack type. As expected, only attacks trigger aborts. In the middle, both privacy policies abort entire episodes when needed, while benign runs continue. On the right, we see the policy mix. Most intervals continue, a few trigger warnings, and only attacks cross into aborts. This is strong evidence the dual threshold policy works as designed. In latency and power, we look at system costs. Latency scales normally with qubit count, and NADGO adds less than 1% in benign operation. Most slowdowns come with the attacks themselves, not from our controls. On the right, power use rises with qubit count. Again, NADGO's overhead is small compared to the attack signal. Overall, we achieve strong protection at a very low cost. Finally, we test sensitivity. On the left, as we tighten the budget, the abort rate for benign traffic falls smoothly, while under attack, the system continues to abort aggressively. On the right, we see that the leakage score maintains high detection accuracy across all margins, almost flat as at above zero point 0.9 AUC. This shows the score is stable and the knobs are predictable. Now let's look at our Tier 2 emulation. The goal of Tier 2 is to bring in more realism. We emulate a heavy hex topology, use calibration data for error rate, and replay real Q logs. We lock budgets and partitions to keep experiments comparable. Now let's examine the emulation results. So the Tier 2 leakage distribution. These plots show the leakage score distributions in emulation. With no privacy controls, the score clusters close to the threshold, leaving little margin. With just a basic kill switch, the distribution shifts slightly, but still brushes against the budget. With NADGO's timing protection, the distribution moves further out, giving us a safety buffer while still keeping aborts precise. In our Tier 2 abort heat map, this heat map shows abort rate across qubit size and attack type. Benign runs stay at 0 aborts, which means no false positives. Attacks trigger rising aborts, about 10% for light timing attacks and almost 40% in the strongest cases. This confirms NADGO acts only when it should and escalates proportionately with attack strength. So thank you. And just a quick takeaway. NADGO shows that operational privacy in quantum cloud can be measured and enforced. It contributes 4 things. 1. A robust per interval leakage score. 2. Hardware-aware actuators for padding, jitter, and routing. 3. A dual threshold enforcement policy at microsecond scale. And finally, a tamper-evident audit trail. Across both tiers, we see strong detection, low overhead, and precise auditable controls. Finally, I would just like to thank my supervisor, Dr. Krishnendu Guha. He's been an amazing help throughout the process. And if you have any questions in relation to NADGO, please email me at samuel.punch@umail.ucc.ie. Once again, thank you for listening.